Hello, welcome to this third video in a mini series. It might be the last video, you never know. You never know. Where I'm using Python, or we're using Python to create particles like these. Let's just run this code on top of the turtle module, the famous turtle module in Python. And I really need to get back to making some Unity videos. So if you're if you subscribe to me to watch Unity, I'm sorry, the last few I've been making Python things. I'll be getting back to Unity and some JavaScript as well. I've got a little idea of making like Perlin noise terrains using JavaScript, which would be interesting. And then I should maybe try that in Python at some point. Anyway, presently what we've got is, yeah, particles which have got friction, they've got acceleration, and when we tap the screen now, we've got some interactivity. We can add some more acceleration to them. So crucially, this video, we want to get collision between the particles working, just like we've got collisions for the window bounds. And what would be nice is when I tap to create more particles. So maybe we'll get to that. The main thing is to get collisions working. So I'm just going to kind of make this up as I go along, like I have done in the last couple of videos. I also think this blue looks gross. It looks horrible. What colour should I make them go when they hit? Is it hitting the left and the right? Maybe I should just leave them. I'll just leave them that colour. Right. Where is that? This just remind us of some of our code. So I haven't looked at this for a day or so. Right. Colour. So if bouncing off the X edges, then that's where I'm changing their colour. I'll make them pink. That'd be alright. I was going to just make them green again. So that's making them pink. And then if it's, so if it hits the top edge, then it goes some kind of green. Okay, so let's do something slightly different. We'll pick a random shade. So we'll do that from the random module. I think I've just used that as R. So I'm importing the random module where I can get randint, the randint function. But I'm using this as R. So then I can choose a random number between like 100 and 255. So rand int between about 100 and 255. I don't want to start at 0 because then it'd be really, really dark. Although now I'm thinking maybe 72. There we go. So we get a random shade of green, and then we'll do the same, but for pink. If they hit the X side, so the left hand side or the right hand side. So I'll do that just above there, and then shade there. Oops, it's a hard hey. Shade and shade. Right. Okay, save the work. And let's just have a look at our colours. And then, oh no, saving took quite a long while. Let's try that again. So while this is playing, I can then have a think about the collisions. So essentially what we want to do is each time we go around the loop, for each particle on the array, we want to iterate over or loop over all the other particles and just say basically are our positions, is a difference between our positions less than, say, our radii summed together, then we must be overlapping. So then maybe just reverse our velocities. So if they're kind of going like this and meet, we check that they're kind of overlapping and then reverse their velocities so they just bounce in the other direction. That would work. So we want to say for every tert, would we do another for loop? We could say check, or I just put collision, which was spelled wrong. That looks better. Collision, and then we want to pass in the current tert that we're looking at, and maybe in collisions we'll call another loop Yeah, okay. Something like that. Right, let's make it here. So define our new function collision. We're passing in a turtle. Okay, we don't have to call this parameter. We don't have to name it the same as what we're actually passing in. I'm just doing it so I know what I'm talking about. I'm talking about a specific turtle. So you could just call this t if you wanted to. And that variable, that local variable local to this function, would take on whatever object you've passed in. That's fine. So I just call it turtle, so I know I'm talking about a turtle. So first, we need another loop. So it's going to look at all the other particle positions. So we'll call it other in BERTs. So we're still looking in the BERTs array. And then, first thing we want to do is say, don't check yourself, because you're definitely going to be overlapping with yourself. And then it would just kind of explode or something. So we want to say, if tert does not equal other, then run the check. Okay, so let's just make a note. Make sure we are not checking particle against itself. There we go. Right, so now we need to grab their positions. So that'd be easy. Let's just say tert x equals tert dot, and was it x coordinate, x core, like that. I think that returns the x coordinate. Then we want to do exactly the same for the y position, and then we want to do exactly the same again for the other particle. So then we've got everything stored in convenient, I'll call that one OX. Okay, I'll call this one TY and TX for the turtle, and then OX and OY. So everything's nice and short, and that needs to be the other turtle's Y coordinate, and that needs to be the other turtles or other particles X coordinate. So now we can check, and we basically want to say, what's the difference between your X position and my X position? Then add that to the difference between your Y position and my Y position. So we might use an absolute function there or something. So we want to say difference on the X equals the absolute value. So if it's negative, just make it positive. Because let's say one of our particles, like this guy, this lighter green one, if his X position is less than this guy's X position, and let's say this is the tert in this loop, and this is the other particle that we're checking against, if we do this guy's position minus this guy's, then the result is going to be a minus number. It might be minus 100, but the difference is just 100. So the absolute function will just change that minus 100 to 100. So it doesn't matter which way round we're checking the particles. Next time it might be this guy minus this guy, and then we'll get our minus 100. Sorry, we'll get our positive 100 result. And it won't matter. The absolute will just return a positive number if we're starting with a positive number. Right. So if that doesn't make sense, it will make sense now when we do the actual calculation. So I'm just going to do my tx minus my other particles x, and then I want to add that to the difference between their y positions, and then we're basically getting their overall difference. And actually, I just want to call this distance. Their distance equals that. Can I put that on a new line? I always try these new things in Python. I don't know how the white space and things work. Right, ty. Maybe if I do introduce that. I don't know. Python uses indents and things, doesn't it, to organise its scoping, so I don't know if that works. Right, And I'm just doing it so that you can see the code. Right, so we've got our distance between them, and then we want to check if the distance between them is less than its radius, so from its center to its edge, plus your radius. So they're all going to be the same. And I don't know what that is because I haven't actually set it. It's just the default size, and it's very difficult to change the size using this version of the module. So let's guess around 20. Let's just put in that figure. So we're going to have to like hard code this. Sorry, I'm going all over the place. Right, so I'll try 20. There we go. Sorry. Keep zooming out. Right, so if the distance is less than 20, then we've got a collision. So what we could do, we've got a choice now. We could just return true and then outside the function deal with what we want to happen, or we could deal with what we want to happen here. So let's just return true. Why not? I don't think I've done it in other videos. So capital T for this Boolean variable. A Boolean will be true or false. And the return keyword just exits the function and returns true or false. That would be good actually, because once we've hit one other particle, or we found the other particle that we've hit, we don't then want to check all the other particles to see if we've hit them. We'll just pick the first collision and then come out of the loop. Else we're going to be checking all the other particles every single time, and that will really slow down our code. So this collision will return true. So what we're going to say is if that returns true, then we've got a collision. So collision, collision here. So I said we could try reversing their direction. So what I really need to do is return which particle I've just hit. So it returns, it reverses its velocity. Let's just try it with this way around first. So we'll just say reverse v, and then pass in that turtle. So we're just going to reverse the velocity on the particle that kind of has the focus, and we're checking it against all the other particles. So reverse v. Let's go and run that. Write that function. So def reverse v, and we get a turtle passed in there as well. Again, I'm just going to call it turt to be consistent. So turt's velocity x times equals -1. So that would just reverse whatever velocity we've got. If it's a minus number, it will become positive, and if it's positive, it will become minus. That rings a bell. Did we do that in a previous video? Where I think we did when we hit the boundaries. Is that what the velocity is called? Is it called vel x? Yes, it is. Did I put a capital letter though? Yes, I did. And I shouldn't have. Okay. So that's quite easy. And then we can we can reverse the y component of its velocity as well. Right, I'm going to save. That takes quite a while to save because my internet's not good in this room apparently. And it's done, and now we can test it and see what bugs we've got. Right, we have got a bug. Syntax error, bad input on line 126. I wonder if that's to do with me putting Python on different lines and it not working. Can I do it here? Like in the middle of an expression? Let's save that. I didn't have to save there, sorry. I should stop saving it and just save it right at the end. So this is a bit quicker. I haven't looked at the time to see how long this video is. Right, no, it's not liking that either. So, okay, we'll put you all on one line until I learn how to do that properly. Don't save it. Okay, and we go. So that's worked. Right. I forgot about this. At the beginning, all the particles are overlapping. So we want to reintroduce something we used here, right? When we were first making this, we quite randomly had a little loop. So this for loop iterates over all of the turtle particles on our BERT list, and then it just gives each particle a random position, or instructs it to go to a random X and Y location. So I've resurrected that zombie code. I had commented it out, and now it should work. Brilliant. So, aha, we have got a collision working. That's great. Lovely. Okay, so a bit of a problem. They definitely do overlap. So 20 was perhaps not good enough. And the other issue we have is if they're traveling faster than, say, 1 pixel, then they can kind of like, within each physics loop, if they're moving like at 10, they'll go 10 into the body of the other, and then be repelled, which doesn't look great. And if I'm honest with you, there's not an easy solution with our version of things. Okay, so first we just wanted to adjust that 20. Maybe try 40, so really double it, and then just see if that looks too far apart. Oh no, that looks about right. So it looks like the radii of these is 20. That looks pretty good. Okay. So yeah, they definitely seem a little bit far apart sometimes when they hit. However, that kind of compensates for this kind of teleporting into each other's bodies, because they kind of like never move faster than a certain amount. Okay, I'm pretty pleased with that. Okay. Oh, now we've got a problem. They can kind of stick together. Oh, and I've somehow stuck this guy beyond the margin because he was travelling too fast. What would be a better way? A better way might be to reverse the forces, or what we could do. Okay, let's just make it up. Let's actually write the code. So we won't reverse their velocities this time. We will write repel. Repel. And what I'll do is just stop the velocity of that particle and give it some random force. Repel, because I guess with a physics system we shouldn't be just changing the velocities instantaneously of our particles. The physics doesn't work that way. The physics always works from changing forces, changing the acceleration, and then allowing that to change the velocity and the position in its own way, using the logic that we've written. So I could say this time tert dot vel x equals 0. So I'm kind of ignoring my little speech, and I am changing its velocity straight away to 0, but then I am adding a force at least. So acceleration x equals random integer between -5 and 5, and then I'll give it a random amount on the y-axis as well. So I'm not doing anything sophisticated there. It'll be interesting to see if that's beneficial, and to kind of get you thinking about what different ways can you have your particles colliding, or rather the consequence of them colliding. What we really ought to do, and it'd be easier if we had proper collision vectors, position vectors, sorry, is to decide, what angle are you hitting one another, and then calculating what it should be. And I think, God, I made years ago a JavaScript snooker program where I calculated the vectors properly. So something you could do here. Right, if you wanted to. So, I'm not very happy with that with this collision logic. But I'm going to I quite like the reverse one. That's not too bad. I'm going to save that while I'm talking. Um, Finally, what should we do? We should see if we can create a particle when we click the screen. So I'm going to look back at a couple of functions here to see what we need to do. So firstly, interaction, we're using this callback like logic. Adrian is our screen object, and it's listening for events like mouse clicks and keyboard presses, and so the on click will fire when there's a click on the screen, and then it will go and run whatever function we put in here. And at the moment we've got explode, which just means add some random force to our particles. So what I want to do as well is write Adrian on click new particle, and then I want to go and write that function now. So to work out how to do it, let's just see where I first create my particles, which I do, oh yeah, here at the start. So it's these lines. So I create a temporary turtle and then basically change its features and then append it to the BERT's list, the array of other particles. So really, I've got everything I need. Okay, so let's try and write this here. So define, what do we call it, new part. And that's going to take, if you remember from the previous video, an x and a y argument. Because when we click the screen, that always passes the x and the y position of the mouse. And that's going to be useful because we're going to use that to set the position of our particle. So, new particle. So let's just copy this code, and it'd be nice, because we're copying code, to maybe write another function that uses that code so that both of these functions, or this loop and this new particle function, can both call that one function so we don't double up our code. But there are going to be some differences. So first we need a temporary object, and it's going to be a new turtle. We make it a circle, we give it a color, we give it an outline with the pen color. Its speed is going to be the original speed of all the turtles. The pen is up so it doesn't draw any lines. I'm going to comment that out so we can see the new particle being created, and then its velocity is going to be 0, 0. It's going to have a random acceleration, and so finally what we need to do is give it a position. So temporary, I think it was set x and set y. Set x to the x position, and then temporary set y to the y position. Is that correct? Right, let's go and run it and find out. I feel like I've forgotten something. So I'm tapping. Oh yes. And I'm getting a new particle. That's fantastic. Right. Interestingly, it looks like they move, the set x and set y kind of like moves them automatically. Sorry, it moves them from the home position to there. So we don't really want to do that until they're fully, sorry, we want to do that straight away before we can kind of see them. So if I just do that there, does that work? Right at the beginning of the creation process. No, you can see there it's just using the default turtle shape, and it's got the default color, i.e. black. It's quite a nice little little pattern. It looks like a robot. It's kind of like a factory. It's kind of like digitally moving or supplying these particles. And you'll notice as we add more and more particles, our program is slowing down because we're building this on top of Tkinter, on top of the turtle module, and our own particles. So it's not the most efficient thing. Okay, right. I'm going to leave this like that. We've got basic collisions working, and we've added some features, and we've done a couple of different functions for dealing with what happens when things collide, and I've not done anything very sophisticated there. Right, hopefully you enjoyed this video, and I'm going to do some more like Unity programming now, and JavaScript, I think. If you've got any ideas though for things you want to see in Python, let me know and I'll get to that. Thank you very much. Have a lovely weekend. Goodbye. Or whatever day it is for you.